Okay, let's get going. So, I'm back. Thank you for bearing with me when I wasn't around last week. I hope it worked out okay for you. In particular, I want to thank you for, doing the midterm in the slightly unusual situation of having it be something that you do on your own. That was an experiment. And, I was relying on you to be responsible and to do the test as if it was in these kinds of conditions, even though obviously you had the opportunity to stretch those conditions. So for those of you who did the test as intended, and I hope that's everybody, thank you, and, I salute your ability to act in a responsible way. We're doing the grading at the moment, and I'll let you know as soon as we have the results for that and everything. Any questions about that? Anything anyone wants to raise? Okay, so let's see, where are we in the semester? Basically, the material breaks up into two sort of separate halves. In the first half of the semester, everything up until now, we've been dealing with these theoretical foundations, the basic mathematical tools we're going to use to understand discrete time systems. And really, for me, that culminates in this sort of graphical interpretation, this visualization of how these poles and zeros in the z-plane give rise to particular behavior of the Fourier transform, which then allows us to understand how our system is going to behave by understanding how it affects the sinusoidal components of any input signal. So basically, we've got that's as good as the tools get, and from now on, we're just looking at various ways of using that kind of perspective and that kind of insight to build different kinds of filters, basically, to do different tasks, which can be useful later on in applications. So in a sense, what we do from now on is it's all just working out the implications of what we've already looked at. But, that can get quite complicated, of course. So, we already started talking about this with these introductory simple filters, and we'll finish off the parts of this slide pack today. And then starting on Wednesday, we'll talk about a few other specific kinds of filters, structures for building filters. And then we have the election day break. And then we look at the filter design for the two different broad classes, IIR filters and FIR filters. Turns out IIR filters, even in discrete time domain, they're using the same math that was worked out for continuous time filters, for analog filters. So I have to learn a little bit about that first. FIR filters were more or less unprecedented for the discrete time implementation, so we'll learn about them directly. And then it's really just a couple of other little topics. The fast Fourier transform, which is an algorithm for calculating DFT efficiently. I've mentioned that before, very important because it makes a lot of these things computationally feasible. And then a little bit of material about interface to continuous time. And then the final project presentations. Let me just take a couple of minutes to talk about the project. As you know, there's both a final project and a final exam, and they both count to 30% of your grade. The final project, as I said at the beginning of the semester, it's kind of the most interesting part for me, and often the most informative part when I'm trying to grade your overall performance in the class, because it's a very good way for me to get a feeling for what kind of mastery, what kind of insight you've got into the topic. It's not meant to be a huge project, right? So it's something that I expect you to do in the last few weeks of the semester. But the sooner you can get started, the better it is. And the more you are into what you're doing in a project, the better the project is going to be. It's going to be easier for you to spend the time on it, and it's going to be more interesting for me to read it because it's more, obviously it's more engaging if it's something that you actually care about and something that's specific and interesting to you. So at this point, you should have a pretty good idea of the kinds of things that we can do with discrete time systems, what the scope of the class is going to be. And so now you're in a position to choose the kinds of project you want to do. So I encourage you to think about that. Right, the submission for the project will be pretty brief, like maybe a 5-page report just describing what you were trying to do, what you did, how you evaluated it, maybe if you got to try and improve it, how you did that. But you know, the substance of it is the actual doing the experiments, doing some kind of work. The only constraint I put on you is that it should be something that deals with real signals. So the point of the project is that you actually get some experience of dealing with, you know, a real signal, something that isn't controlled and artificial, or something that has some of the problems you like to encounter in the real world. Because that is the part you're not going to learn from me lecturing, but you're only going to learn from trying it out, the kinds of problems and other factors, sort of messy factors that come up when you're dealing with real-world signals. So that's the goal. I would like to, so you can also do normally I say you can do the projects alone or in pairs. I would encourage you to do pairs this semester because we have a big class and then there'll be fewer projects in the end, but whatever makes sense for you. It's quite interesting. It's valuable to work in a pair as well because then you additionally exercise the skills in working, collaborating and negotiating with someone else about how to get work done. But whatever works for you. I would like to have some idea of what you're going to do for your project. Firstly, it's a good idea to let me know, like via email, for instance, just so I can give you feedback on whether the scope of the project is about right. And we can avoid some unfortunate situations later on if you let me know what you're thinking about, so that if it is something that I see problems in, I can alert you to potential problems there. It's given that I've seen a few of these projects go by, I should be hopefully able to advise you on whether I think it's going to work out well or not. So please think about, whether you're going to put together a team and what project would be interesting to you. And if you have several different ideas, then feel free to send me an email suggesting each of them, and I can discuss them for you. There's a list of ideas, project suggestions on the website. They're not very good, but I never know quite how to rework them. They were just, a few years ago, I sat down, I wrote down a bunch of ideas that were projects I was interested in at the time. But please don't take those as kind of like, oh, this is, a closed set. It's just to give you the ideas of the kinds of different projects that I was thinking about and the kinds of different things that you can do. The idea is to do something fairly open-ended, something that's, doesn't have to be the final word on any single topic. Just something where you can exercise what you're doing. Of course, Darwen is also available to discuss and advise on project topics. Any questions about that? And then the final project presentations, these are optional, but if you've done something that you think you could make an interesting presentation to other people in the class who are interested in, I encourage you to do this. This is normally well subscribed and a very enjoyable part of the semester. Okay. All right. So we in this slide pack we've spoken about a couple of very, very simple kinds of filters just to get into the idea of, okay, a filter is typically a filter family, you know, a set of, say, second-order FIR filters or two-pole IIR filters, which we may have a general shape, but the shape can vary. Typically, there'll be some parameters we can set to change the shape, and then we'll have some attribute like the cutoff frequency, and then we'll end up with a design equation. Once we've got a family chosen, we can set the parameters to achieve some particular functional parameter that we care about. And then, you know, there are different classes of filters for different things we want to do. The high pass and low pass are kind of simplistic, but once we get onto band pass filters, even with just two poles in a band pass filter, this is already a kind of a useful filter. You can pick out a range of frequencies, you can vary the width of the range of frequencies, and you can correspondingly vary the amount by which it selects a particular frequency, the gain of that frequency compared to its neighbors. But there are many more complicated filters we can look at, which we'll see as we move forward. The band stop filter, I mean, this is actually, by putting a 0 exactly on a frequency, for some frequency, you can, in theory, completely eliminate it, right? Of course, a single frequency is a sort of idealized concept because it means a sinusoid that is constant amplitude for all time. But, you know, as we've spoken about the effects of transients, ignoring the effects of transients, you can completely remove a single frequency with one of these notch filters, and that's tremendously useful. I had this situation where we had hum on a recording, right? We made a recording, but there was some mains hum, which was at 60 hertz and then 120 hertz and 180 hertz. Put together a bunch of these notch filters. It's amazing how much you can do with something like that. It goes from being almost unintelligible to something that's quite usable. So these are low-order filters, two poles, two zeros. We can make higher-order filters, which typically have better characteristics. One way is simply by repeating the filter, which will be like raising the response to a power, which makes the valleys deeper, so it can improve the response. There are better ways to build higher-order filters, but it's just to introduce the idea that there's a very simple way of doing it. And so this was kind of my summary slide to help you sort of get the big picture in preparation for the midterm. It's not a terribly clear slide because it's got so much on it. What I like about it is it does sort of have everything on it, and that it makes the point that we've dealt with these different domains, the time domain, the frequency domain, with a couple of aspects of each, and that they're all linked together. I think after I did this, I figured out there are even, you could draw more lines in here, but just the idea that we've learned these different ways of thinking about signals and systems. Okay, so that brings us to today's lecture. And there are a couple of things we're going to talk about. The first is just the general idea of ideal filters. So we've gotten to the point where we understand that a particular discrete time system will have some properties, and then a particular application may lead us to want particular properties. And so we can try and find the system that has the properties that we want. And the way we've sort of talked about filters, the simplification is like, well, there are some frequencies you want, some frequencies you want to get rid of because they're not informative. And so ideally, we want a gain of 1 for the frequencies that we want, which means that they're passed unmodified without any kind of change, and a gain of 0 for the parts that we don't want, so they're completely eliminated. I've sort of said that, well, you can't really do that in general, but let's just think about this for a moment. So that if we had some frequency response like this, we could plot it, the magnitude response, to look like this. It would be a set of frequencies where the gain is 1, and then a set of other frequencies where the gain is 0. And this kind of frequency response is called a brick wall filter. So it would be a brick wall low-pass filter. And so, well, why can't we have this? Why not? In particular, if we have the magnitude response, then, well, we know that specifies the, if we had the frequency response, it specifies the impulse response, because it's just the frequency response, it's just the Fourier transform of the impulse response. So why don't we just take this ideal magnitude response, we can give it 0 phase, then it becomes a full frequency response, and with no phase modifications, that's the ideal phase response. We can just take its IDTFT and we get a realization of this ideal filter, which sounds exciting. So here's our frequency response. It's pure real. It's 0 between minus pi and minus omega c, and between omega c and pi, and then it's 1 from minus omega c to omega c. So we're passing both positive and negative frequencies so that we can get a real impulse response. So the impulse response of this is just the IDTFT of this, which is just this integral of this times the e to the j omega n. This is obviously just means that we change the range of the integral here from minus omega c to omega c. And this thing is an integral we've seen before, that basically we can, the integral, the unlimited integral of e to the j omega n with respect to omega is 1 on jn e to the j omega n or something. We take the limits, and we get this sine x on x, this sinc function coming out. So that's kind of, that's interesting. You might have expected something to blow up when we were doing this, that if this filter is not really something we can have, then maybe something would go wrong. Nothing's gone wrong. We've got an actual impulse response. It's an impulse response we can plot, right? This is what it looks like. It's the sinc function. We saw it before, sine x on x, so it sort of has a sine x function. It decays away as 1 over x, and then around 0 it has this kind of lobe where it tends to, x on x tends to 1 in the middle. Yeah?
So sine x on x, but your x is omega c n. And
yes.
And your
yeah.
pi n.
So it's not sine x on x, it's sine omega c n on pi n. But if we normalize this as, omega c normalized to pi times some normalization factor, then it'd be pi times that, and then we could put that on top, and so it'd just be a scaling factor at the front here. The number in here is important because that's basically the period of the sinusoid in here. So as omega c gets smaller, the ripples here get further apart, right? So that controls it. But the fact that it's not strictly the same value on the bottom is just a scaling factor on the amplitude. It doesn't really do anything interesting. It's just the important part is that it's sine of something divided by something. So the thing that's proportional to the variation. Okay, so now we've got this impulse response for this ideal filter, meaning that if we have a signal and we convolve it with this impulse response, we get exactly that frequency response that we wanted, where it'll keep some range of frequencies and eliminate some other range of frequencies. But now we begin to see why this is a practical problem. This is an infinite impulse response. Okay, fine, we've seen infinite duration impulse responses before. Anything with a pole has got an infinite impulse response. But this is infinite in both directions. So not only does it, if in theory, if you had this filter, you put an impulse in and it carries on forever, it actually would have started, you would have had to start infinitely before the impulse arrived as well to get this full impulse response. So it's non-causal, and it's infinitely non-causal. And even though we've seen other systems that have infinite responses, this is one where there's no closed-form feedback way to get this response. The only way we could implement this is by actually having a delay line with a bunch of taps coming off it to implement each individual point of this response, which would be a very long FAR filter. And of course, then we wouldn't be able to make it infinite. We'd have to make it out to some length, and then we'd sort of have to forget about the bits beyond that. So what we'd have then, I mean, this is a truncated version of sync, right? I only plotted it out from -20 to 20 points here. So this is the kind of thing we could actually do where we just chopped off the ends and forgotten about them. Although the ends, they're not too small here. They'd still be visible even on this linear amplitude plot. But then this is what the impulse response would look like. And so for a signal which was a single impulse, well, firstly, we'd have this big delay to make it causal. But secondly, the impulse would get spread out over this long response. And this amounts to time domain ringing. So you may have seen ringing in various systems that have very abrupt frequency domain changes in their frequency domain response. And this is one of those. And so this is the problem you get. And so what's happened is that by specifying very, very tight frequency domain characteristics, by saying it's going to go from a gain of 1 to a gain of 0 and essentially no gap, we end up with very, very poor time domain characteristics, which is to say an impulse in the input gets spread out a great deal. So something that happens very precisely in time gets blurred out, gets smeared out over a wide range in this kind of nasty way with these multiple local maxima. And this is very typical, that because of the complementary nature of the time domain and the frequency domain, if you try and limit in one, then you end up sort of splurging out in the other and vice versa. So here, we're trying to be very precise in frequency, and we end up blurring out in time. It works the other way around. If you try and make it very tight in time, then typically you end up with a very blurry frequency response. So the message is, yes, we can mathematically figure out what an ideal low-pass filter would look like, but it's not practical. Just as an aside, we mentioned this idea of like, well, if you want to get a range of frequencies where the response was exactly 0 for all those frequencies, the only way we know how to get a 0 in a system is to put a 0 on the unit circle. This FAR filter would have a lot of zeros, infinitely many zeros if we implemented the whole thing. And so it would be like having infinitely many zeros on the unit circle and stop band. And when we truncate it, we start getting, well, now we've got a finite number of zeros, so we get the zeros, but then there are little ripples in between. So we lose the ideal behavior. We'll actually go back and look at that truncation filter in a little bit, just to see what happens. We can analyze that quite nicely. But this is, right now, all we're saying is, okay, I see that I see where the problems are going to come out here. So that basically means that, well, it's a mistake, or it certainly gets you into trouble to try and specify your frequency response too tightly, too ideally. Instead, what we do is we say, okay, we recognize that we're going to need a little bit of wiggle room, a little bit of flexibility in our specifications. And so then we have filters which are specified with these kinds of relaxations. So in our filter, we have a pass band and a stop band, frequencies we want to keep, frequencies we want to get rid of. But instead of saying that the gain has to be exactly 1 in the pass band, we say we want the gain to be approximately 1, but we'll allow a little bit of deviation. So here on a dB scale, a gain of 1 would be 0, but here I've plussed it so it's saying, well, maybe plus or minus 1 dB is okay. As long as it stays within 1 dB of 0, that would be okay, for instance. In the stop band, ideally, we want to remove the energy completely, which would mean a gain of negative infinity dB. But it's like, okay, well, maybe we can't get that for all frequencies, but if we just say there's some worst case attenuation, if we say the attenuation is at least 40 dB for all those frequencies in the stop band, that'll be okay, and that'll be something that maybe is easier to realize. Typically, it will go to negative infinity for some frequencies, but there'll be these bumps in between, which we want to try and limit. And then we can allow ourselves a little bit of space between the pass band and the stop band. We expect the frequency response, the magnitude response, to be this continuous curve. And so we sort of recognize that if we're trying to get from a gain of minus 1 dB in the pass band to a gain of minus 40 dB in the stop band, say, it might take us a little bit of frequency, a little bit of omega to get there. So we'll have a transition band, which is this range of frequencies where we're not trying to control the gain. by settling for these relaxed constraints, we can end up with a filter that has lower order, right? So rather than being incredibly long FIR filter, we can make it some more sensible length, or we can actually do it at all in the case of the sync impulse response, which is basically less computation, less memory, fewer multipliers per point, generally cheaper. Also, by allowing the frequency domain to be a little bit soft in its behavior, we end up reducing the pressure on the time domain to spread out. And so we can get better time domain properties. We can end up with a filter with some sensible compromise between its time domain spreading and its frequency domain sharpness. And by having a system that has this little bit of flexibility in it, we can there are a broader range of tools, of procedures we can use, which will actually give us results of this kind, because we're looking at a broader range of possible responses. So that's just the we're gonna see these kinds of relaxations show up when we start talking about filter design techniques. But that's just a preview of the kinds of things we're going to do and why we have to relax that way. Any questions about any of that? This is just so, okay, introducing the idea of ideal filters, and then what we do when we don't want, when we accept that we can't have an ideal filter.
Good question.
Yeah.
So with the transition,
Yeah.
can we affect how fast that transition?
Right. So with the transition band, all we're saying is, well, we recognize they're going to be separate frequencies for the edge of this pass band and the edge of the stop band. Now, if we have a design procedure, we expect those to be parameters. And so we can say, no, I want them to be really, really close together. And typically what will happen, or you can say, no, I don't mind, they can be far apart. If these are parameters, you can set them where you want them to be. You can try and set them to be the same frequency, although typically that's going to get you in trouble. But what happens is, if you have a design procedure, then often you can try and set this minimum rejection to be as low as you like, this ripple to be as narrow as you like, and this transition band to be as small as you like. But what's going to happen is, well, if you try and make all of those things better at once, that one of the things that's going to come out of your design procedure is what the order of the filter is, how expensive the filter is going to be, and it's going to get more expensive. That an ideal, in the best case, you've got a design procedure where you plug in these parameters. It tells you the filter, including, well, you have to use, this is the family of filters we're going to use, whatever, our filters, but you're going to need 100 poles or something like this, and it's like then you have other problems. But at least it says, well, in theory you could do it. It's just it's going to cost you. Turns out in practice you normally can't do it. If you get a system with a lot of poles, then they become numerically very sensitive, and so you can't even build it if you want to. But given ideal computation, you could do it. Okay. So shooting for ideal magnitude response in sense of getting stop bands where no energy comes through for a whole range of frequencies, that's basically not practical. But in the phase domain, it turns out that the ideal phase characteristic, which is no phase shift for any frequency, is something which is either attainable or close to attainable, in the sense that we can build a filter which maintains the alignment between the phase of all the frequencies, which is to say, maybe a sinusoid experiences a particular delay, but the delay is the same independent of frequency. If we don't have that, if we have we hopefully in the lecture I didn't deliver, which I gave you the video of, we talked about different kinds of delay that the systems can impose, phase delay and group delay. And group delay is this idea that if you have frequencies that, as you change in frequency, the phase changes by some linear function of frequency, by some slope, then a set of frequencies in that region that are sort of, corresponding to an envelope, they'll experience a delay. As long as the slope is linear, then the delay is constant, and the signal is basically undistorted. It's only when you get curves in the phase response, and so now you can't fit it by a single delay, and the signal becomes distorted because different frequency components of the signal are being delayed by different amounts. So if we can obviously, if we have a phase response of 0, that's great, and that's called a zero-phase filter. And we can build those, although typically they're not causal, but they can be, sometimes we can use non-causal filters. But if we have a constant delay of d samples independent of frequency, that means that the phase function would be, would have to have a slope of d for all frequencies. So minus d omega is such a function, right? It's just a straight line with a slope of minus d. This is called a linear phase system because its phase is a line. And this is something we can actually build. These things are realizable. So what we're saying is the frequency response is going to be some magnitude response here, a pure real part, which if that were all it were, if that were the entire frequency response, then it would be a zero-phase filter. But we're going to allow it to have this pure phase term, which is linear in omega, e to the minus j d times omega, which is effectively a delay of d samples. D could be non-integer. And if we had a system like this, and we weren't operating in a strictly causal regime, so we could actually run the system and then get the entire signal out, we could just shift it in time shift it back by d samples, and then it would become zero phase. So in that sense, if you can have a linear phase system, you can often simulate the result of a zero-phase system. So let's see a couple of ways we can do this. One way, which is kind of interesting, is by reversing the time axis. So think about this system here. We have x of n coming in. We have some system, h of z, gives us an output v of n. We then take v of n over our entire time base of interest. So we have to have a limited time base here. Then we just flip it, so we get u of n, which is v of minus n. So we take the last sample, make it the first, and vice versa. We take this new time reverse signal, we pass it through h of z again. We get a new signal out, w of n. And then we reverse it again, and we get our output. So between the input and the output, we've had two time reversals. So roughly speaking, we're back in the normal time axis sense by the time we get out. But we've applied h of z twice, once in the forward sense and once in the backward sense. And the idea is that if there's a frequency which is delayed by a certain amount when it went through in the forward time sense, when we put it through in the backward time sense, it'll get delayed by the same amount, but now time is looking the other direction, so that delay will shift it back to zero phase. And so we can get an overall cancelling out of the phase response, although the gains of these two things will compound, right? Well, actually, if we're reducing its amplitude by a half here, we'll reduce its amplitude by a half again here, so it'll be an overall gain of a quarter. Let's just do this using our identities, our transform domain identities. So v of n is x of n convolved with h of n, which means that in the Fourier domain, v of e to j omega is h of e to j omega times x of e to j omega. Time reversal was actually an identity we saw when we looked at the DTFT, that if u of n is equal to v of minus n, then reversing the time axis is actually the same as just reversing the omega axis. That comes out of the DTFT expression. So u of e to j omega is v of e to the minus j omega. If v is real, if we're dealing with real inputs and real impulse responses, then v of e to j omega will be complex conjugate. All real signals have to have their negative frequency parts be the conjugates of their positive frequency parts. So v of e to j omega is equal to v conjugate of e to j omega. Then we pass that through h of n again, so we get w of e to j omega, which is, this is u as the output here. U is equal to v conjugate of e to j omega. So w is equal to h times u. Then we do time reversal again, so y is equal to w conjugate, assuming, again, everything is real. but W is H times U, U is V conjugate, and so we get this, and V is H times X. So we get H times X in here, conjugated, times H again, and then conjugated again. And when we work that through, these conjugates cancel, so we get X of eta j omega, but we get H of eta j omega times H of eta j omega conjugate, which is the magnitude of H of eta j omega squared. So this is our overall response, that Y of eta j omega is X of eta j omega times magnitude of H of eta j omega squared, which is, what we expected, that the phase portion of H has been reduced to 0. This is a 0 phase response. This is the actual frequency response, but the frequency response is pure real, because the phase that was added in here was subtracted out here. But the overall gain is now the square of this individual filter, because we basically, if we think about each sinusoid, it goes through this filter twice. So its magnitude is modified by the gain of the filter twice, so we get the square. But this is nice. We can take an H of Z with any kind of phase function, any kind of nonlinear weird phase function, and it automatically cancels itself out, nulls itself out. The only problem is that we need to, in order to do this time reversal step, we need to have all of time available at once. And so it's sort of something that's easier to do with like images, where you have the whole signal there to begin with. Much harder to put into a box that you can feed an audio signal through. Yeah?
Can we only use this type of filtering if the impulse response is real?
Can we only use this kind of thing if the impulse response is real? No. I mean, if it wasn't real, this part wouldn't work out, right? But you could, the point about it being conjugate symmetric is that, that in a sense we're using the conjugate symmetric part of the frequency response to cancel out the phase. And so you'd need to have a second filter that somehow applied that phase response in the opposite direction. So it might be that the second filter wouldn't actually be the same filter, but you should be able to, but hopefully you'd be able to come up with one that did what you wanted in terms of only reversing the phase of what you started with, without, it wouldn't have to be a completely separate filter design. It seems that there are two ways that the system could be complex. We could either have a system with a complex impulse response, or we could have a signal that was itself complex, or we could have both. And I think we'd get different, and because we're saying what we want is that this thing, which is the product of these two, we want that to be complex conjugate, or we want it to all work out at the end. So I don't know. I mean, it's sort of hard to. The situations in which you have complex frequency responses, you have to mean something by that, right? It's like, why are you suddenly, in general, we introduced the imaginary axis just to as a mathematical convenience, so we could use the complex arithmetic, but not because it didn't really have any meaning in terms of the original signal. Now, sometimes you can actually talk about, you can imagine complex signals, particularly in like, high frequency signals where you're talking about a component which is now around some carrier, and so it has a phase and an in phase and a quadrature term. So then you can, I don't know. I'm sure that there's something like this you can do without relaxation. I'm not sure.
But so for most practical purposes, we will be just using real?
Yes. In most cases, we always deal with real signals, because that's the practical situation. Yeah. Okay. That's one way of doing it. There's another way we can do it, where we can actually get. Yeah. Sorry.
So by doing this time reverse filtering,
Yeah.
Actually altering the transfer function itself. Like instead of getting h of z, you're getting h of z squared. I mean, the magnitude response is actually squared.
That's right.
So,
So if we
how do
so
get over just getting the magnitude
Yeah.
response and letting go the phase?
so your observation is that we start off with some filter. We've applied this filter. We've managed to take away its phase effect, so it's now got a zero phase effect. But we haven't got the filter anymore. We haven't got its magnitude response. We've got its square of its magnitude response. So it's like, wait, I didn't want that. I wanted the actual filter just with zero phase. So what do? Well, that would be the design procedure. If you know what magnitude response you want and you want zero phase, then the trick is to design some h of e to j omega whose magnitude response is the square root of what you want, right? Which
Wouldn't that be difficult with actual like capacitors and inductors on the road?
typically that's not. I mean, it depends. How much harder would it be to design have some magnitude response and design its square root rather than its direct form? Typically, it's not that big a deal because the magnitude response you want, is some kind of thing with some passband in here. On a dB scale, right, it might look like this. But on a dB scale, the square root is simply dividing it by 2. So now we just want to design a filter that looks like this, where this is, if this is some function h of omega, say, so it's a magnitude response, then if this was just, I don't know, q of omega, so I'm now plotting the dB response, then what I actually want is a system where it's q of omega on 2. So if this is now 0, say, then that sort of looks like the same kind of problem. It's just a slightly shallower filter that I'm trying to design. And very often, with these filters, the ultimate slope depends on the order of the filter. And so it's quite easy to design a filter with half the slope. You just use half the order of the filter. And of course, that makes sense. Now, to get this original filter, we're using this half-order filter twice. So the overall order is still whatever it is, the sixth-order filter to get our 36 dB per octave or something like that. OK, so there's a second way to get linear phase or, constant delay filters. And that's to use FIR filters with a constrained shape. Basically, symmetric FIR filters is the trick here. And this is something that was a novelty when discrete time processing was first introduced, because suddenly you could specify your impulse response point by point, just by having a delay line and have a set of gains come off it. So you could build these impulse responses with arbitrary structure and arbitrary symmetry, and then this idea of linear phase actually amounts to the same as having a time symmetry in the impulse response. And so you could build these, which you could never build with causal feedback systems with poles. So that's the general idea. We're going to have a system, finite impulse response, so it's finite length filter, but the impulse response is going to be symmetric in time. It turns out that there are two kinds of symmetry here. Symmetry with a single point, a symmetric point in the middle where we've actually got a sample, or symmetry where you don't have a point in the middle, where the middle point is midway between two samples. There are no other ways you can do it. If you skew this so it's not symmetric, then you won't get the same values here. But it can either be at 0 or a half. And this is an odd length filter. So an odd length filter, you have one point in the middle, then m points over here and m points over here, so you get 2m plus 1 points. Or you just have m points and n points, so you get 2m points. So you have odd length and even length symmetric filters. It turns out if you have anti-symmetric filters like this, where the one side is the negative of the other side, then you also get something which is close to a linear phase response. We'll say it's not quite linear phase, but well, the phase is linear, the group delay is linear, but it's not a linear, it's not just d omega. So these are also fall into this family, and again we have the same thing whether you have a center point or not. If you do have a center point, it has to be 0 here to get, because it has to be its own negative, and here it's not observed. So that gives us 4 types of filter, and they are known as types 1 through 4 of the linear phase or symmetric FIR filters. So let's look at the properties of one of these. Of course, now that if I specify an impulse response, in particular if I put a constraint on it like symmetry, then I can work out what that means in terms of its Fourier transform. So type 1 filter, odd length, symmetric. If the length is odd, that means the order, which is 1 less than the length, right? The number of zeros in this case is going to be even. But here's our constraint. We're saying it's symmetric, so we're saying that h of n is equal to h of big N minus n. So the first point is the same as the last point. The second point is the same as the one before the last point, like this. And then because n is even, we have n on 2 is an integer, so we have h of n on 2 equal to h of n minus n on 2, which is h of n on 2. So the point in the middle it doesn't have a symmetric partner. It's just whatever it is. But with this constraint, we can now think about working out the DTFT. So we can plug in this h of n into the DTFT equation here. And the way we can use the symmetry is we can pair each of these points which are the same. So rather than having to specify all L individual points, we can just specify n on 2 of them, and then we've got every value in there. And so we can pair them up. Well, we have the h and n on 2 point, which is unique, but then we have twice each of the h of n, which is equal to h of n on 2 minus n, times the e to the j omega n plus e to the j omega big N on 2 minus n. We can take out the center point. The sine parts cancel, and we're left with just the cosine part. Right? So if we rearrange this, take out this middle term of each of our e to the j omega n, e to the j omega n on 2 minus n terms, we're left with a conjugate pair of e to the j omegas like we've seen before. And so if we write them both as cos plus j sine, then the j sines cancel out, and we're just left with the cosine, twice the cosine term. So what this is saying is our DTFT, our frequency response, is equal to this linear phase part. This is not by design. This just fell out of, but it's not, we didn't force this, but it fell out of the expression. And then a pure real term here, right? There are no complex values in here, which is determined by the values of the impulse response. But its variation with omega depends on cosine omega n, where this n is now which point in the impulse response we're looking at. So basically building a function of omega out of these basis functions, which are these cosine functions. So our frequency response is going to be built up out of different amounts of these different cosine functions, and the different amounts are the values of the individual points in the impulse response. And as the impulse response gets longer, we're going to have higher numbers of n to go up to, right? The summation is from n equal 1 to big N on 2. So we're going to have increasingly rapid versions of the cosine functions to build it up from. So this part, which is just the magnitude response, is it's like we're going to build it up as a Fourier series out of cosines, a Fourier series in omega out of cosine bases, and then the longer the symmetric impulse response we use, the more Fourier terms we can include. So the finer the structure of the magnitude response. We're familiar with the idea that using the Fourier series, we can approximate any kind of shape, in this case, any kind of magnitude response. But if we only use a few terms, then the approximation is fairly blurry or smooth. If we want to get a sharper, a more accurate approximation, then we need to use more terms. But the key thing is here, this mathematical thing where we turn these eta j omegas into cosines because we've got symmetric pairs of them, which will then cancel out the sine parts. You see that? You see how the math works out? If not, try it out because it's not complicated. I just didn't put it all on the slide. So now we have this symmetric impulse response where his Fourier transform we know is going to be some kind of real part made out of cosines. Here I've plotted it in dB scale. So even though this is only a fourth order filter, we've only got cosine omega and cosine 2 omega in here. It doesn't sort of looks a little bit sharper than that just because the log nonlinearity. The phase response, of course, we're just saying is minus d times omega. That was coming from this this part here, where d, the delay, is equal to n on 2, which is the midpoint of the impulse response here. That's the effective delay, is it sort of takes an impulse at 0 and then turns it into this blurred out impulse centered on 2. So it's like it's effectively delaying everything by 2 samples. Of course, the linear phase function, which has got a slope of minus 2, will wrap around this thing. We have the principal values between minus pi and pi. So here it wants to go from 0 to minus 2 pi for omega equals 0 to pi, but omega equals 0.5 pi, it wraps around and comes back up the top. But that's just the ambiguity, the 2 pi ambiguity in the phase function. So again, we'll see a lot of phase functions that look like this. They're straight with these jumps in, but the important part is the straight part, saying that the slope is locally constant. The slope is constant for all frequencies, apart from the discontinuities. Well, this is just a filter, an FIR filter. So we're used to taking our filters and thinking about them in the pole zero domain. It's a finite order filter. It's not that different from what we've looked at. So where are these zeros? The constraint that this thing is symmetric, we can actually put this into the, we can take the Z transform here. The reversal in time is turning h of z into h of 1 over z, and then the shift by n points is just multiplying by z to the minus n. Z, you have to be a little bit careful to get the sign of the n in here correct, but it turns out this is the result. What this means is if there's some 0, which means there's some value of z for which h of z is 0, so if the 0 is zeta, then h of zeta is equal to 0. We're saying that h of z is equal to z times h of 1 over z. So if this part is 0 and this thing is not 0, then this part must also be 0. So that means that for any 0 that you find, the reciprocal value of z must also be a 0. So if I have a 0 here, some r and some theta, then 1 over that is got a radius that's 1 over r, and it's going to have an angle that's the negative of that theta. So this point and this point is saying if this one's 0, then this one has to be 0 too. That's just the consequence of the symmetry in time. Now, for a system that has a real impulse response, we also have to have conjugation of all the roots. So if we have a 0 here, then and it's a real impulse response, then it's going to have a 0 here. If it's also symmetric, then it's also going to have zeros here and here. And so for these linear phase, real valued FIR filters, we have these constellations of 4 zeros. So we have a single 0, then we have its conjugate, and we have the reciprocals of both of those, the reciprocal radii. So if this is at, this is at 0.5 from 0, then this will be at 2. If this is at 0.9, then there'll be another one at 1.11, right? 1 over r. If the 0 is on the real axis, then obviously it doesn't have a conjugate, so we just have a pair like this. If a 0 is on the unit circle, then its reciprocal is its conjugate. So we already have the reciprocal there because of the conjugate from the fact that it has to be real. So we can get pairs of zeros here, either on the real axis or on the unit circle. But for any 0 that's not there, then they have to come in groups of 4. Which means that, this is a fourth order system, right? You have to have at least 5 points in your FIR to have 4 zeros. But as the order gets larger, you can have many sets of 4 zeros like this involved. So these symmetric FIR filters have these very characteristic pole zero diagrams. Of course, no poles here because this is an FIR filter. It's only got zeros. So that's all we see. So that's type 1. Type 2 is even length symmetric. So it's got same shape, but now there's no point in the symmetry point is in between two samples. Everything looks the same, except now when we try and write this out, there's no separate h of n on 2 point here because n on 2 is odd. L is even, so n is odd, so n on 2 is non-integral. But we can do the same thing of pulling together these pairs of symmetric points. When we do that, we end up with this. We have to divide out the value in the middle, which is now halfway between 2 points. So we end up with this a half, n minus a half coming out. And here's our linear phase term, which is also, because n is odd, is going to be a half sample delay. And so now, again, we have a set of cosine basis functions that we're going to be able to build up our magnitude response out of. The real part, the magnitude response here, is just a set of cosines, but they're cosines of n minus a half for n equal 1 to some value. And so whereas the lowest one in the type 1 filter was like n equals 0, so it was just a constant value. Here, the lowest, the smoothest one is this thing here, which actually is just a half cycle in the minus pi range. And again, it's this thing we saw before that it seems like this magnitude response is periodic in 4 pi, not 2 pi, because it's omega times a half. But because of the sign flips, it actually ends up being periodic in 2 pi because it has to be, because it's a DTFT. But the real part is periodic in 4 pi. And the phase takes care of the rest. We end up with these basis functions, and now they're basically like odd multiples. They're odd harmonics. So we have this one that completes a single quarter cycle, and then the next one is this one that completes 3 quarter cycles. 1, 2. What does it do? No, sorry, this one. 1, 2, 3, and then we have 5 quarter cycles. 1, 2, 3, 4, 5. So they're like a set of odd harmonics. And we notice that all of them go through 1 here, all of them go through 0 here, which means that no matter what we scale these coefficients, whatever we scale these basis functions to be, we're always going to get a 0 value here at omega equals pi at the highest frequency we can represent. Yeah?
Can you just explain once again how the cosine comes out that way? Cosine n minus.
How it comes out? Okay, so we're doing the same thing that we did before. We're going to take these two values of h of n, which have to be the same, and we're going to write down the Fourier transform. H of e to the j omega is the sum of h of n e to the minus j omega n. We're going to take these 2 points out, and we're going to group them together. So it's going to be h of n times e to the j omega n plus h of big N minus n times e to the big N minus into e to the j omega big N minus n. But those two values are the same, so it's h of n times e to the j omega n plus e to the minus j omega n plus e to the minus j omega big N minus n. To make those, to get rid of, when we have the difference of 2, or the sum of 2 exponentials like that, we can divide out their geometric mean, and then we end up with e to the plus and e to the minus, and we can cancel out. But when we do that, what we have to divide out is halfway between 0 and n, which is n on 2, but that's a non-integer number because n is odd. So we end up, I mean, we could, depending on what we write it in terms of here, we could get different numbers in here. But when you work it through, you end up with this n on half. This is like counting from the middle. What I'm doing here, right, is I'm taking the middle point and stepping one, different numbers of points away. So it's a slightly weird indexing into h, but that makes it clear that we end up with all these n and a half values as the frequencies that we're getting. I didn't go through the math, but hopefully I've pointed you so you can do it and get through it. Okay, great. So now let's look at this in terms of its frequency response and its pole zero diagram. So here's our typical even length symmetric FIR filter, type 2 filter. The magnitude response, again, it's some shape that we can build out of these Fourier terms, but these odd harmonic cosines. But it'll be some shape, but it will always have a gain of negative infinity dB at omega equals pi. It'll be linear phase, again, but the phase now, the slope is some non-integral number of samples. In this case, it's the delay here is 2.5 samples. So when omega gets to pi, the phase is 2.5 times pi, which is like here's 1 pi, here's 2 pi with the continuation down here, and then here's the extra 0.5 pi, right? So it's 2.5 pi, which after you've wrapped it round actually makes it just minus 0.5 pi. And here's the pole zero diagram. Now the symmetry still means that we have these sets of these constellations of 4 zeros at conjugate reciprocal locations. But if we think it through, we have this situation that at z equal minus 1, which is this point here, omega equals pi, then we have h of minus 1 has to equal minus 1 to the n times h of minus 1, right? 1 over minus 1 is still minus 1. We've got this z to the minus n term here. N is odd, so minus 1 to the n is minus 1. So we have that h of minus 1 has to equal the negative of h of minus 1. And so that means that's the constraint that h of minus 1, which is h of e to the j pi, has to equal 0, which is the same as saying there has to be a 0 here in this system, which is the same as saying this filters with this kind of symmetry, will always exactly cancel out a sinusoid that completes pi radians per sample, which is a sinusoid that goes 1, minus 1, 1, minus 1, 1, minus 1. Right? That's the highest frequency sinusoid we can represent without aliasing. And you can sort of see that. This is the most simple even length symmetric FIR filter. And it's just the summing of two adjacent points. And so if the points are always 1, minus 1, 1, minus 1, then if you sum two adjacent ones, you always get 0. And it turns out that if you add more flanking things, you still get the same thing. That this is, the 1 minus 1 is always going to be, negated on the opposite halves. And so the two halves are going to cancel out. So you're always going to get a gain of 0 at omega equals pi. So you've sort of seen that like 4 different ways now. But that's the classic hallmark of an even length FIR filter. With an odd length filter, let's see, with the regular type 1 filters, we did have an opportunity to build a gain that would have a gain of 0, build a magnitude response that would have a gain of 0 here. So with the type 1 filters, we can put these zeros in different places, and we could put them here as well. So it's not that we can't do that. But with a type 2 filter, there's no way we can build it without having a 0 here. Okay, so the type 3 filters, the remaining filters are the anti-symmetric ones, where we have the, h of n is equal to the negative of h of n minus n, right? Here I've shown the first one's all positive, the second one's all negative. In general, they can be either way, but they're going to be the opposite of each other like that. If we do the same kind of analysis, well, here we have a middle point. H of n on 2 is an integer, so h of n on 2 is an actual value, but it has to be its own negative, so just like in the previous case, has to be 0. And then if we do the thing of working through the, gathering the terms that have the same h value, now it's going to be, well, they have the same h value, but the sign is flipped. So it's going to be, if we count out from the middle again, it's going to be h of e to the j omega n on 2 minus n minus e to the j minus j omega n on 2 plus n. So now, this is after we've, if we take out the e to the j omega n on 2 term, then we get e to the j omega n minus e to the minus j omega n, which is, if we do the cos plus j sine expansion, that cancels out the cosines and leaves us with the 2j sine parts. So now we have the h of e to j, the h terms, the h of n terms as coefficients for a set of sine basis functions. And we get a j coming out, a constant j, which is also just a pure phase term, right? It's a pure pi on 2 rotation. So here's our phase term, which the variation with omega is linear, but it's not proportional to omega. And then here we have the pure real magnitude response part, which is built out of sine functions starting with sine omega. Looking at the phase term first, the actual phase of this, right, this is the e to the minus j omega n on 2 is a linear phase rotation, of omega n on 2. And then the j part is a phase rotation of plus pi on 2, independent of omega. So here's the phase, pi on 2 minus omega n on 2. So it's basically a pure delay, but it also has this pi on 2 phase shift, basically a quadrature phase shift built in, which is sometimes useful, although most of the time it messes up the shape of your function. But sometimes you actually want a quadrature, a constant phase shift for all frequencies, and that's how you can achieve it. And then here's our set of sinusoid basis functions again. It's like a Fourier decomposition, but now they're all in sine phase, the ones we get, which means that they're going to be odd functions. We're building it up out of odd functions, so the overall response is going to be odd. Doesn't matter that much because we're mostly just interested in its magnitude. But because we're using sine functions, which are all 0 at 0 and all 0 at pi as well, we end up with a family of magnitude responses, which is going to have a 0 at pi, just like we had with the type 2 filters, and a 0 at 0, which is new to this filter. Which means in our pole 0 diagram, we're going to have zeros here and here. Right? That's what, if the gain is 0, that means there was a 0 on the unit circle at that particular frequency. The phase response has this slope of negative n on 2, but it starts at pi, right? So it starts at pi on 2. It's pi on 2 minus n on 2 omega, which is for positive pi for here and negative pi for here. So there's this kind of discontinuity in phase at 0, because actually you can't, a phase shift of pi on 2 corresponds to a delay of a quarter of a cycle. If your frequency is 0, your cycle length is infinite, and so you can't delay it by that much. Fortunately, the gain is obliged to be 0 here, so we don't have to deal with the problem of what does it mean to delay this very, very low frequency by a quarter of its cycle. So we sort of hide this discontinuity in the phase function under this 0 in the magnitude response. That's how you can sort of get away with it. Again, if we think about the constraints of the symmetry and the reciprocals, then we get these points that both of these values have to be 0. So we get the 2 zeros emerging just from that consideration. So, like I say, when you use these functions when you want this pi on 2 phase shift, that would be, otherwise you'd be much better off with an actual symmetric filter. The final type, type 4, even length anti-symmetric. Basically all works out the same, except like the even length symmetric filters, we end up with this half offset in the basis functions that we use. So now we're using sinusoidal basis functions for our magnitude response, but they're overall period 4 pi in omega. So now we still have the 0 here, but now we don't have an obligatory 0 at omega equals pi. So we end up with a family of responses that look like this. They have a 0 at 0, but they could have whatever shape you can do with however long they are in terms of the number of sinusoidal basis functions. The pole 0 diagram will have a 0 at 0, but then otherwise everything will be in these conjugate reciprocal sets. And again, the phase response is linear with this pi on 2 offset. Okay, so just to summarize again, we have the 4 linear phase FIR filters. This is the most flexible, the symmetric, odd length symmetric, because there are basically no constraints on magnitude response apart from the fact that it has to be built up out of a finite set of cosine bases. This is the most flexible one that also achieves a pi on 2 phase shift. Pi on 2 phase shift means that you've got to have a gain of 0 at DC because you can't delay a DC signal by a fraction of its wavelength, because it doesn't have a wavelength. Wavelength is infinitely long. But apart from that, you can make it whatever shape you want. We understand how the magnitude responses are built up out of sinusoids, cosines, or sines, up to an order depending on the length of the filter. So as we get longer filters, we get higher order sinusoids to work with, and so we can build more complex shapes. But as we understand from the Fourier transform, from Fourier series, the actual shapes we can build up are otherwise unconstrained. If I do have a full set of cosines, well, cosines are always going to be 0 phase, but then magnitude responses are always going to be symmetric. Magnitude responses for real systems are always going to be symmetric. So that's not a big constraint. But then we can make whatever shape we want. It's just the level of detail is going to depend on how long we make that filter. So it's a very, very general set of filter responses we can make. And yeah, we have our ideal phase response that the delay experienced by all sinusoids is the same. And so the shape of the function, which is the composition of the different sinusoids, is not distorted as a result of that. Any questions? Okay, so in a couple of weeks, when we actually get onto the design tools for FIR filters, they will be for these kinds of filters. Right now, we've sort of seen, well, yeah, if you can express it in terms of its sinusoids, we can build it up. But there are different ways we might want to express that, which we'll see later. Okay, I'll see you on Wednesday.